Hi everyone. So next we want to discuss our implementation of bagging. So we are using car seats data from ISLR library, and we are using random forest package for random forest function. So bagging can be done by random forest function because random forest and bagging are basically the same except for the number of predictors used in each tree. So remember that we are predicting sales data on by other variables. So we are using car seats data, and we are using only training set to train this tree. So we specify TRN. So TRN is the 200 observations. So index for 200 observations out of the entire 400 observations. Then MTRY, so this is the number of variables, predictors used in each tree. So in fact, this car seats data only have 10 predictors. So this means we use all predictors. So that is bagging. Then we want to get some importance measure. So we get the importance is equal to true. So it uses the out of bag method. So it takes some time. So if we omit this, then we may make it a little faster. Okay, so but still the bagging is pretty fast in my laptop. Bag 1, so what's the result? So actually we use the 500 trees and we take average to get this bag, to this bagging. And the mean of squared residuals is 2.77. Yes, and the 66% of variabilities I explained. So maybe we can see the importance of bagging. Then you can see the importance here. So this means that, for example, that if we drop the shelf location predictor, then actually we have increase in mean square error by 67%. So this is very important variable. And the other ones, the maybe price or competitor's price, are almost also the moderately important. And education actually is almost a noise, so it makes error slightly larger in this simulation. So the second column is almost the same thing, so increase in node purity, but the node purity is basically the residual sum of squares. So basically it's the same as mean square error. But the first column is calculated based on out of bag measure, but the second column is just in sample data. So the first one is more accurate description of the power of each predictor. Okay. So also you can make a graph of this variance measure. So that is made by the variance IMP plot function. So variance importance plot function. Then you can get this. So you can see that now it's ordered. So shelf location is most important, and these variables are less important. So this is by the increase in node purity. But this is actually from in-sample data. So the first one is more accurate description of the predictors. So this is basically the bagging and its graphs. So now that we want to calculate the training, the mean square error, and the test mean square error. So we want to define the predicted values. So predicted value for training set, PRN. So this is predict bug 1, so bugging the random forest object, and the new data is equal to car seats training set. So this is the training. And then remember that in the last video, the video for regression tree, that we defined the actual, the TRN. You can see the previous video. So, and we want to compare actual versus the predicted. So this is the plot. And actually this time it's really good. So last time we have 9 levels for regression trees, and we have some positive correlation, but this time it has much higher positive correlation. So we should expect a better MSE. Okay, so we calculate mean of difference between predicted and actual. A squared error, then take average. So this is MSE for training. So this is only 0.478. So this is very good. So remember that last time the regression tree, so this was about 2.5 to 2.6. And linear regression stepwise procedure, we got 1.05 or something. So, but this time 0.48, so it's really small. But this is training error, so the test error is different issue. So we just do the same thing for test observations. So we want to predict for test error, so use the same object bug1, but we use the training set here. Then we want to plot the TST. Remember that the actual TST was defined in the previous video for regression tree. So this is test performance, and it's much worse than the training set. So this is disappointing, but the relationship isn't very good. But maybe still a little better than the regression tree, in the sense that we have more smooth the plot. So last time we have just 9 different levels, but maybe possibly correlation is higher for this one. So we want to calculate the MSE for test set also. So MSE, TST, so MSE for test set. And actually this is 2.9. So last time the regression tree, this is almost 5, actually a little more than 5.0. Okay? And linear regression, that was 1.05. So actually it's still much worse than linear regression, but we have a lot of improvement over the simple, basic, the regression tree. So sometimes the random forest works even better than linear regression, but for this data set, it performs not that good. Okay, so this is the bugging. Okay, so see you then.